Number 10, so we have contact process, and we investigated at 200 kilopascal and 700 Kelvin, and we found out the value of that is Y. Okay, I think I get it now. Okay, you repeat it at 1000 kilopascal, but the same temperature. So the same temperature, but higher pressure. And then you have a new Kp, which is Z, okay? So Kp is an equilibrium constant, okay? Equilibrium constant. There's only one condition that can change value of equilibrium constant, and that is temperature. Only temperature can change equilibrium constant. What do we know about this reaction? It still carries out at the same temperature, 700 Kelvin. So what can we say? Temperature hasn't changed, so therefore equilibrium constant will not change. Your equilibrium position can change, your equilibrium yield can change when pressure changes in this reaction, but equilibrium constant, the value of Kp, will remain the same because your temperature is the same. One of the most important concepts, but one that students always get wrong. Okay, so question 11. So you have Maxwell-Boltzmann distribution, you have hydrogenation of alkene, you have it in the absence of a catalyst. So when you add nickel, which is a catalyst, and you learn hydrogenation of an alkene back in GCSE and also O-level, it's towards the end, when you want to, it's one of the reaction of alkene to make margarine, okay, to make margarine, vegetable oil, okay, so you use nickel catalyst together with your hydrogen gas as your reducing agent. So when you use a catalyst, the shape of the Boltzmann distribution does not change because only temperature can change your Maxwell-Boltzmann distribution shape, okay, nothing else. But you have a new lower activation energy when you use a catalyst. So activation energy would have a new lower value, meaning you have decrease. Alright, so there's option C there. Question 12, this is something that you can get from the data booklet, okay, because you are given atomic radius and you're also given ionic radius from the data booklet. So you can get it from the data booklet. They don't tell you, but really you know all this data are available in the data booklet, yeah? But you should also know this value, okay, because from sodium to chlorine, this is atomic radius. I don't know the actual value, but I know the trend decreases. I should be expected to know how to explain this because this is what they ask in a paper 2 theory setting. You can watch my topical playlist under I think atomic structure to explain atomic radius across a period for an atom. When I have the ion, the cations will be smaller than the parent atom because you have lost electrons and you have more protons and electrons. You experience stronger attraction, okay, compared to the parent atom, which doesn't have a charge because you have equal number of protons and electrons. But on the other hand, your anions would have bigger radius than your parent atom because you have gained electrons. Also, what is important is these three have lost an electronic shell. When you think about it, Na plus, Mg2 plus, Al3 plus, all of them have neon configuration, which is 1s2, 2s2, 2p6. You have lost the 3s, you have lost the 3p subshell, and meaning to say you have lost the electrons filling in those orbitals, alright? So this one would definitely be much smaller than this one, which occupy n equal to 3 shell. For sodium and magnesium atom, you occupy the 3s. For aluminum, you also occupy the 3p. So magnesium atom is bigger than magnesium 2 plus. So that is true, this is incorrect. Sulfur anion is bigger. Sulfur anion is bigger than the atom. So that's option B there. Question 13, this kind of question has gotten popular over the years, yeah? So we want to plot electronegativity against atomic radius. In fact, I've just shown you in the previous question. Atomic radius decrease across a period, chlorine all the way to sodium. So this is atomic radii. What do we have? We have sodium, magnesium, aluminium, and silicon. So we know sodium is the biggest, so we know atomic radius. So this is the biggest, this is the smallest. So on our x-axis, we should expect the smallest to be silicon, aluminium, magnesium, sodium. So this one is fine on the x-axis. Silicon, aluminium, magnesium, sodium. This one is fine on the x-axis. Silicon, aluminium, magnesium, sodium. This one is fine on the x-axis. This one is not fine on the x-axis. This is saying that aluminium is bigger than silicon, and that is not true. Okay, we already crossed out one possibility there. Another one is electronegativity increases across a period. So we are saying that sodium, magnesium, aluminium, silicon. This one is the most electronegative. This one is the least electronegative. So silicon is the most electronegative. On the y-axis value, silicon would have the highest value. Silicon is not the highest value, so A is out. Silicon has the highest value, so I'm pretty sure B is the correct answer. Let me just double check. Sodium is the highest electronegativity, and that is incorrect. We already established D was incorrect based on the x-axis. So we're right. It has to be B. Alright, that's how you tackle this kind of question. Think about each trend separately, and then try to think about the points on the graph. Number 14, you have trends in physical and chemical properties of group 2 elements and their compounds, of course. What shows a decrease from magnesium to barium down group 2? What is decreasing? All right, between the element and dilute hydrochloric acid, when you have M plus HCl, if you have a group 2 element M, you have M2 plus and Cl minus. Lowest common multiple, LCM, primary school, I think primary 4 when I did mine, you need 2 of these because 2 times minus 1 balance out 1 times plus 2. Okay, you get MCl2 and you will get H2, you get 2 HCl to balance the equation. Just like that, yeah? So we have a redox reaction here because this is M plus M0. This is M plus 2. So this and this need to lose electron. The metal lose electrons. Because the metal loses electrons, when you go down the group, it's easier for your group 2 valence electron to be lost. They become more reactive towards water. They become more reactive towards acid because you become more readily to lose your electron. You become more readily to be oxidized. Oxidation is loss of electron. Involve loss of electron, all right? Hang on. I shouldn't circle that. I just said that the rate will increase because it become easier to lose the outer shell electrons down group 2, right? So A is actually wrong, okay? The hydroxide become more soluble down group 2. This is a statement that you need to be able to state in AS. Same deal as that. The sulfate become less soluble down group 2. The easiest thing to remember about is barium sulfate, very insoluble. Barium hydroxide, very soluble. Just by thinking about one of them, you can get the other trend already, okay? So the hydroxide become more soluble. That is not what you want. You want decrease. So the sulfate become less soluble. Okay, so that is actually what you want. Temperature of decomposition. The carbonates, well, the carbonates of group 2, you can label as MCO3. And also the nitrate become more thermally stable down group 2. So because they become more stable to heat, it requires higher decomposition temperature, higher temperature required before they will decompose. So although these trends are required to be stated at AS level, at least for paper 1 and paper 2, but then you'll be expected to explain it in your A-level paper. When you reach to A2, there will be like quite a few free mark kind of questions because you can prepare for those questions and you can go through those with my tutorial videos on an A2 Group 2 Extension Chemistry. However, just with any chemistry, if you just memorize stuff without really following the story, it wouldn't make sense to you at all. So when your time comes, I hope you will get to understand the beauty of that chemistry. Question 15. You have calcium oxide, you add it to water, and then you form calcium hydroxide. You filter it because some of them might be insoluble. Filtrate is the soluble stuff. So meaning to say, X is the calcium hydroxide. So this is called saturated solution because you dissolve as much as you can in it, and this is actually lime water. Lime water you use to test for CO2 is a saturated solution of calcium hydroxide. When you bubble it through that, you get a wet precipitate because, like I said, test for CO2. Calcium hydroxide is a base or is an alkali. You react it with CO2, which is an acidic oxide. What you're going to get is you're going to get a salt. The salt of CO2 is what you call CO3 2-. So what you're going to get is CaCO3. And to balance the equation, well, whatever you write in A level, you have to balance it. CaCO2, get away one oxygen, becomes CaCO3. You also form H2O as well. Alright. So filtrate X with carbon dioxide. You get a calcium carbonate and water. That is precisely correct there. None of the other one makes sense at all, yeah? Number 16, you have element X with cold dilute sodium hydroxide. You get chlorine containing products. This is your classic disproportionation as stated in the Redox changes syllabus. If it is not under Redox changes, then it will be under Group 17 Chemistry. Okay, make sure you can spell that completely. One species, which is the element, is both oxidized and reduced into the two products. This is with cold and dilute aqueous NaOH. So you only stop at chlorine -1 and chlorine +1. That is your ClO-, that is your Cl-. You started at Cl2 plus NaOH, give you NaCl plus NaClO plus H2O. This is chlorine 0. So chlorine 0 going to -1 is decrease of 1. 0 to +1 is increase of 1. So your -1 is balanced out by +1. So it's just 1 and 1. And therefore, we don't write the 1 in front if it's just 1 and 1. So there's 2 sodium. So there's 2 sodium. So there's 2 chlorine. There's 2 chlorine. There's 2 hydrogen, 2 hydrogen, 2 oxygen. One of it goes there, one of it goes there. Right? So they just want what are the oxidation state of chlorine in Y and Z. I don't know whichever one is whichever one, but there is Y and Z. Doesn't matter which one is which one. It's chlorine -1 and +1. So it's -1 and +1. You get +5, which is ClO3-, or in the form of the sodium salt, if you have hot concentrated NaOH plus Cl2. Okay, that is another equation that is much harder to balance, but you can balance it in a couple of those topical MCQ questions on redox changes, as well as on Group 17 Chemistry, that you can find in another playlist, and something that I've already recommended very highly in the earlier part of this tutorial video. So next question, you have a powder. It's either single sodium halide or a mixture of 2 sodium halide. Okay, so you dissolve that in water. You add a silver nitrate. You get a pale yellow precipitate that tells you silver iodide is formed. When you add corn aqueous ammonia, the precipitate partly dissolves. We know AgI does not dissolve in concentrated NH3 at all. So what does this information tell you? Partly dissolve. It means that this is not just AgI. Okay, therefore it must be a mixture of 2 sodium halide. If it is just sodium iodide, which means you get silver iodide when you add silver nitrate, because it will form silver iodide, If that is the case, when you add corn ammonia, there will not be a decrease in the mass of the precipitate. There will not be a partial dissolving of the precipitate because AgI does not dissolve in corn ammonia. The fact that it dissolves means that it must be a mixture. It must be silver iodide plus something else, okay? It must be sodium iodide plus something else. And we know AgCl, AgBr dissolve in concentrated ammonia. So it has to be, it's not sodium iodide only. It's not only one substance, it's a mixture, definitely a mixture. And between the sodium iodide, so it's got sodium iodide, this one has no I minus, so this one is wrong, which means D. Okay, in fact, the other possibility is it could be sodium iodide and sodium bromide, because it's very difficult, especially in paper 2 or even paper 5 or even paper 3, they could ask you, how come it's very difficult to tell whether it's chloride or bromide? Because silver chloride is white, PPT, silver bromide is cream, PPT. Between these two colors, if you have yellow in the background, there's no way you can tell which one is which one, really, okay? When you have a mixture, there's no way you can be able to tell whether it's white or cream when you have a yellow in the background. So if you have another possibility, it could be a mixture of sodium iodide and sodium bromide. That is another possibility. But they don't give you the possibility, right? This is definitely wrong because there's no iodide present, whereas you get a yellow precipitate. Question 18. You have ammonia reacting with H plus there. So when you think about this, this is a dative covalent formation. From the lone pair, it takes in the proton. When it takes in the proton, it donates both the lone pair of electrons to the H plus. Then the charge is now on the nitrogen, which has 4 covalent bonds. And we can say this ammonia has accepted a proton. This is acting as a base, and then this is the ammonium ion is a Bronsted-Lowry base. That is incorrect because it has accepted a proton that become the conjugate acid. This is a term stated in the acid and base specification. It says candidates should be able to use the term acid and base as well as conjugate acid and conjugate base. Alright, so make sure you can cover that very well. So which statement about this species involved in this reaction is correct? The ammonia molecule contains dative covalent bond. That is incorrect because it is the NH4 plus that has a dative covalent bond. So this is the dative covalent bond. Both the electrons in the covalent bond come exclusively from the nitrogen. The ammonium ion is a Bronsted-Lowry base as it accepts a proton. That's incorrect. It's a conjugate acid because going the other way, it can donate the H plus. Okay. The H and H bond angle changes from 107. So that is 107 degree because that is trigonal pyramidal with 3 bond pair and 1 lone pair. And here it becomes 109 degree because now you have 4 bond pair and 0 lone pair because you have 4 sigma bond with no more lone pair around the nitrogen, so they repel equally. This is a tetrahedral. Okay, so it doesn't change to 90 degree, it changes to 109 degree, which means the answer must be D. And we can tell the number of electrons surrounding each nitrogen atom does not change because you started with 1, 2, 3, 4, 5, 6, 7, 8. This is dative covalent bond, so it's 2 electrons on the nitrogen. 2, 4, 6, 8 is still the same. Okay. Number 19. So you have nitrogen gas reacting with hydrogen gas, giving you ammonia gas. They said that only 15% of the nitrogen reacted. So we have information on the nitrogen gas. We want to know something about ammonia. So if we have the usual conditions, the mole of ammonia is to the mole of N2 should be 2:1. 1 mole of N2 should give you 2 mole of ammonia. But this situation is different. You only get 15%. So in reality, you only get 15%. So this is times 0.15 because you only get 15% of what you get. 1 mole should give you 2 mole, but you only get 15% of what you get. Alright? So that's for the ammonia. You only get 15% of what you get. 15% means 15 over 100. That is 0.15. On the right hand side would be the actual mass of the ammonia divided by the molar mass of the ammonia, because the top bit is for the mole of ammonia. This is based on the reaction, the stoichiometric equation. 1 mole should give you 2 mole, but you have 15% yield only, so I times 15 over 100. This is the actual mass of ammonia obtained based on the 15% yield. At the bottom is 2 dm cube of nitrogen, 2 divided by 24. That is the mole of nitrogen gas. So working that out on the calculator, 2 times 0.15 times 2 divided by 24 times 17. So you can do it step by step, but I have just rearranged everything. Well, I mean, I could show you what I mean by rearranging everything. But that was what I pressed in my calculator, and I got 0.425 gram. And there's a 0.425 gram as an option there. Alright?